For number 9, I'm going to do integration by parts. So notice that u is going to be logs first. So therefore dv is x dx. And because my u isn't going to go to 0, I'm not going to be able to use the shortcut and use the table. So I'm going to go ahead and take du and the antiderivative. So remember, my integration by parts formula is u dv is equal to u times v minus the integral of v du. So I'm going to have x squared over 2 times ln of x minus the integral of v times du. So notice my x are going to cancel. So I'm going to have 1/2 times x dx. So 1/2 is a constant, so I can just bring it down. And the antiderivative of x squared is x squared plus 2. So my antiderivative is going to be x squared over 2 of ln of x minus 1/4 x squared plus c. For number 10, I'm going to go ahead and break both of them apart. I'm not going to do u substitution because that's not going to work. The simplest thing to do is to simplify. So I'm going to have 1 minus 6, 5 x to the negative 1, or just rearrange that one. So 6/5 times 1 over x. So the antiderivative of 1 is just going to be x. The 6/5 comes down, and the antiderivative of 1 over x is ln. For number 11, we're going to find the Maclaurin polynomial. So the Maclaurin polynomial is centered at x equals to 0. So we're going to find f of 0 first. So sine of pi times 0 is going to be 0. Then we're going to take the derivative. So the derivative of sine is cosine, and then times the derivative of the inside. So f prime of 0 is going to be pi cosine of 0, which is just pi. So the second derivative is going to be the derivative of cosine, which is negative sine, times the derivative of the inside. And when we substitute 0, well, sine of 0 is just 0. The third derivative is going to be the derivative of sine, which is cosine, times the derivative of the inside. So the second derivative at 0 is going to be negative pi over 3 cosine of 0, which is negative pi over 3. So my polynomial, or Maclaurin polynomial, is going to be 0 plus pi x plus 0 pi x squared over 2 factorial. I just like to put the 0 anyway because I like to go 0, 1, 2, and then the next one's going to be 3. Times x to the third over 3 factorial. So my polynomial is going to be pi x minus pi to the third over 3 factorial x to the third. So there's my third degree Maclaurin polynomial. For number 13, we're going to test for convergence or divergence using each test. Actually, we're not going to use each test. We're just going to identify the test. It doesn't matter which test we use. We just need to identify which of the tests we actually use. So for the first one, I'm going to use the nth term test because I noticed that if once I use the nth term, the limit as n goes to infinity of n plus 1 over 3n plus 1 is 1, which is not equal to 0. Hence, by the nth term test, this series is going to diverge. Okay. For B, I noted that this is a geometric series where r is pi over 6, which is less than 1. Hence, it's going to converge by the geometric series test. Okay, for C, I noticed that I can take the integral of this so I'm going to let u be x squared, so du is x dx. So my x's are going to cancel out. So I'm going to have 1 over b of negative 1/2 e to the u. And the integral is going to be negative 1/2 e to the u, and I'm going from 1 to b. So if I substitute u back, I get negative x squared from 1 to b. And remember, I have the limit as b goes to infinity. So if I substitute this, I get e to the negative b squared minus e to the negative 1. Well, this is 1 over e to the b squared. And notice that as b goes to infinity, this is going to go to 0. So this is 1/2 1 e. So it converges. So therefore, this is also going to converge by the integral test. For D, I always try to use the nth term test. But notice if you use the nth term test, this is going to equal 0. So that doesn't going to tell me anything. So what I'm going to do is I'm going to compare this to 1 over 3n. So the only thing that the limit comparison test says is that I need to make sure, or the direct comparison test, I need to make sure that this is bigger than this, which it is, because the denominator we're adding 1. So notice that this is a harmonic series or a p series where p is equal to 1, which is not greater than 1. So it's going to diverge. So I'm not going to be able to use the direct comparison test because since this is going to diverge, I need to show that this is going to be smaller. So what I'm going to do is I'm going to use the limit comparison test. So I'm going to show that the limit as n goes to infinity of 1 over 3n plus 1, 3n over 1, so notice that this equals to 1, which is greater than 0. So because we're using the limit comparison test, we use this. So if the series that we compared it to diverges, then the series diverges. If the series converges, it converges as it equals the limit. So this is going to diverge by the limit comparison test. Okay, so now E, I notice that it's an alternating series. Okay. So in the alternating series, I have to show that the limit as n goes to infinity of the absolute value is equal to 0, which it is. The only thing that I have to show though is that it's a decreasing series. So what I have to show is that the nth term, nth plus 1 term, is less than the n. And you're going to notice that it is, because the denominator here is going to be a lot larger than this. So this is a decreasing series. So by the alternating series test, this converges. So one of the things about a series of which test to use, usually when I have a factorial, the best test to use is the ratio test. So we're going to go ahead and use the ratio test. So we're going to have n plus 1 factorial over 10 to the n plus 1 times the reciprocal so we're going to have 1 over 10 times with the n plus 1 and the n. So notice that when you subtract 1, you're going to have n. So these are going to cancel. All I'm going to be left with n plus 1. So as n goes to infinity, okay, this is going to go to infinity. So therefore, since it goes to infinity by the ratio test, so since it's equal to infinity, this is going to diverge by the ratio test. Okay, and then the last one, so anything to a power, we always want to use the root test. So we're going to take the limit as n goes to infinity of the nth root Okay, so notice that they're going to cancel. So we're left with n plus 1 over 2n plus 1. And then this is going to be equal to 1/2. And since it's less than 1, this is going to converge by the root test.